for this seminar. Let me start with some motivation for this seminar. So as you know, and I guess I see some more experienced people in the audience that knows well. Maybe Antonio, who is very young, doesn't remember that much. But before the LHC started, we had some great hopes for what the LHC would give us. So we expected the LHC to be something like this, like a big jungle full of many interesting things. We expected to find supersymmetry. We expected to find extra dimensions, even black holes, compositeness, all sorts of stuff, many different things. However, when we opened the box and we look inside, what we found was actually more similar to this. We found basically nothing, a big desert, and then just a small palm tree in the middle of it, which is, of course, very important, is the Higgs boson, but nothing else. So I think in this audience, I don't need to motivate this further, but there's still reasons to go beyond the standard model, even though we have found nothing at the LHC. And for me, personally, I would think that the main reason for that is actually neutrinos. There are many things in the standard model that are not understood, and all of them, not to say all of them maybe, actually are related to the lepton sector. There are many things in the lepton sector that are not understood. So for me, neutrinos is the main motivation to go beyond the standard model. And, you know, neutrinos have given us many, many big surprises since the very beginning. This is a story that I'm sure you know, but you know that when in the 20s and in the 30s, there was this big problem about beta decay. The measurements of the different spectra of beta decay show that actually the spectra was continuous, meaning that the different electrons could have different energies. And that was not understood because according to just conservation of energy and momentum, the energy of the electron had to be always the same, just a straight line and nothing else, not a continuous spectra. So the person that came up with a solution to this was Pauli, who wrote this famous letter in 1930 proposing the hypothesis that maybe there was another particle that we cannot observe, and that particle is taking away some of the energy and the momentum that is not that doesn't balance correctly in the reaction. I find this very interesting because well, I don't speak German, but I'm pretty sure that some of you can read the letter. And in any case, you can find translations online. And Pauli is kind of embarrassed because he's proposing the existence of a particle that we cannot observe. So for him, I think he was feeling dirty by proposing this. And it's funny because nowadays we propose new models with many new particles, basically every day in the archive, and we feel fine. So it seems that our mentality has changed a lot since then. So, well, this was a funny story, that is true. And also, that could serve as motivation for neutrinos being messengers of some new physics, new discoveries, some interesting stuff. And as I said, there are many open questions in the lepton sector. We know that neutrinos have masses because we have observed neutrino oscillations, but we don't know the origin of neutrino masses. Also, we don't know if they are Dirac or Majorana fermions. Since they have no electric charge, they could be Majorana fermions, and they are the only fermions in the standard model that have this possibility. All the others have to be Dirac. We don't know the absolute scale of neutrino masses because we haven't measured it yet, even though there are several experiments that are trying to do that. For the same reason, we don't know the mass ordering, whether they are ordered normally or in an inverted way. We don't know if there are more than 3 neutrinos. If there are more than 3 neutrinos, we know that they should be probably sterile, meaning that they don't couple to the standard model gauge bosons, because otherwise they would have been observed at lead, for example, in a Z boson decays. And finally, we don't know if there is CP violation in the lepton sector. And again, there are several experiments trying to answer this question. So I think there's plenty of physics here to have fun with. And with this, I finish the introduction. Let me now concentrate on a particular type of models for neutrinos, which are radiative neutrino masses. I think it is a very well motivated class of neutrino mass models. I hope to convince you about that. And then I will devote the rest of the talk to a specific model, the Scotogenic model. It's a particular model of this type, of this radiative type. And it's very popular because it's very economical. With just a few ingredients can explain a lot, not only neutrino masses, but also dark matter, as you will see. And also because for me, and this is again my personal taste, I think there are also many variants of the original model that are actually very interesting. So for me, it is also interesting to go beyond the original model and consider variations of the same idea. So let me start with radiative neutrino masses, so this type of models that I want to convince you is interesting. First of all, I have this very ugly plot that I made with just no technology at all, a very simple plot, where I have all the known particles, the standard model particles, with their masses here represented in logarithmic scale. You see here, the heaviest one is the top quark, then you have the Higgs boson, the gauge bosons, and so on, the Z and the W. Then you have the fermions in red, and the quarks in red and the charged leptons in blue. And finally, here below, I assign a mass of 1 electron volt, which is actually a bit bigger than the current limits. Neutrinos are actually a bit lighter, but nevertheless, for this plot, it's okay. You see the big distance between the standard model particles and the neutrinos. So there is a big gap, and we don't have an explanation for this if we believe that all of them come from the same origin. If it's just the Higgs mechanism behind, then it's hard to understand why there is a big gap between the masses of the particles, the fermions and the gauge bosons and the Higgs and so on, and the neutrinos. One would expect that if they all come from the same origin, they would be more or less together. So the neutrino looks special. For that reason, when we have a model for neutrino masses, not only we need to explain the origin of neutrino masses, but also why they are much lighter than the rest of the particles. That's basically the two questions that we need to address in every neutrino mass model. So if I concentrate on Majorana neutrino models, and this is what I will do for the rest of the talk, I can write a very general expression for neutrino masses. And it's given here. It's not my expression. I took it from this paper that I actually like very much. And it's very simple. In any Majorana neutrino mass model, you can write something like this for neutrino masses. There are several terms, several factors that are multiplied here. The first one is just what you get in the minimal setup. Since Majorana neutrinos get their masses at dimension 5, you know, the minimal operator that leads to neutrino masses of Majorana type is the so-called Wigner operator that is dimension 5. So you need to suppress by 1 over lambda, some heavy scale, typically given by the mass of a heavy particle. So this is the minimal thing you always have with Majorana masses. You have Higgs per square divided by lambda. Okay. But then you may have additional suppression factors. For instance, in some models, lepton number is approximately conserved. This means that there is a parameter, for example, a mass parameter, that is very small. And when this parameter goes to 0, lepton number is restored. This is, for example, what happens in the so-called inverse seesaw, that is also a very popular model. In that case, it's the so-called mu parameter. So in that model, when that parameter goes to 0, lepton number is recovered. Because of that, neutrinos would be totally massless in that limit. And that implies that the resulting neutrino mass has to be proportional to that parameter, or to some power of that parameter. If that parameter is small, then automatically you get a suppression. So this is very nice. Another way to suppress neutrino masses, and this is the one I will explain later, is by loops. If neutrinos are generated, the mass of neutrinos is generated at some loop order, then you will get for each loop 1 over 16 pi squared. And this again makes neutrinos lighter naturally. This is also welcome. And finally, it may happen that neutrinos get their masses not at dimension 5, but at a higher dimension. In that case, the power of this BEV divided by lambda is higher. And since the BEV will be much smaller than lambda, this will again introduce some suppression. As I said, I will concentrate on this possibility, the possibility of loops. So this is typical in models in which you have lepton number violation, so lepton number is broken, but neutrinos don't get masses at tree level. Since lepton number is broken, eventually they will have to get a mass. But if it doesn't happen at tree level, that will happen at some loop. And there are many models of this type, many of them. To the best of my knowledge, there are models in the literature that you can find on arXiv up to n equal 4. But most of them are n equal 1 and n equal 2, I have to say. N equal 3 and n equal 4 are already a bit weird. Not so many examples. Very interesting though, very interesting. Also, this suppression mechanism can be combined with other suppression mechanisms. For example, you can also have some approximate lepton number conservation. So you don't have to marry to one particular suppression mechanism. You can have both. And finally, and this is very interesting, this type of models sometimes have a dark matter candidate. And it's not hard to understand why this happens. Sometimes you need a symmetry to forbid neutrino masses at tree level. And that symmetry can also be used to stabilize a particle. So that symmetry will be used to stabilize the dark matter candidate. So in order to illustrate this general class of models, let me show you some historical examples. The first one that I wanted to show you is the C model, which comes from Anthony C, who proposed it in 1980, many years ago. And what I like about this model is that it's super simple, very simple. In addition to the standard model, you just have a second Higgs doublet and a singlet. The singlet, here I call it S, has hypercharge 1, and that's enough to produce neutrino masses at the one loop level. So it's very interesting that you don't need to add new fermions. Just with scalars, you get neutrino masses at the one loop level. I don't want to explain more about this model because I will concentrate on a different example, but just wanted to show that just a very simple addition makes the job, which is very interesting to me. Very similar to the C-Babu model. So the C-Babu model, again, introduces only scalars. So you have a singly charged scalar and a doubly charged scalar, S and K. With that, you get new Yukawa couplings to the standard model lepton doublet and to the standard model lepton singlet. Also, together with a cubic term among the scalars, is enough to produce neutrino masses at the two-loop order. Again, only with scalars, nothing else. And also, I wanted to make this point that it's funny because people call this model the C-Babu model, even though it was proposed many years before by Cheng and Li in a paper. So it's interesting that the names stick, but sometimes they are not very fair. Anyway, it's a very interesting model, and I think it was rediscovered later because of its simplicity. And finally, just to give another example, at the three-loop order, you get this AKS model. It's one of the known models at three loops. Here you have both scalars and fermions. You have a second Higgs doublet and some singlets, and also you have some right-handed neutrinos. Let's call them right-handed neutrinos, some singlet fermions. Since you have these singlet fermions, these right-handed neutrinos, if you didn't have any additional symmetry, these guys would have a Dirac mass term with the normal neutrinos, and then they would eventually produce a mass for neutrinos at tree level. In order to forbid that, you need to add a new symmetry, a set to symmetry, under which these guys add on. And because of that, that Dirac mass term is forbidden. Again, assigning proper charges to the other particles, plus, minus, and minus to the other three scalars, you get neutrino masses, in this case, at the three-loop order. And, well, this model is very interesting also because due to the set to symmetry, you also have dark matter. And this is something that we pointed out some years ago. Since you produce neutrino masses at the three-loop order, you need very large Yukawa couplings because the suppression by the three loops is very large. And because of that, you may have problems with lepton field violation. When the Yukawa couplings are large, typically processes like mu2 gamma and so on are dangerous. So this is something that we pointed out recently. It's a very constrained model because of that. So let me now concentrate on the Scotogenic model, which is the main subject of my seminar. I would like to mention that this model is known in the literature with different names. For example, some people call it the inner doublet model, but I think this is not a correct name because in the inner doublet model, you don't have neutrino masses. You just have the inner scalar. So it's like a smaller model, a subset of this model. Also, some people call it radiative seesaw, which is a better name, but still there are many radiative seesaws. So I think it's also not very specific. And finally, I have seen also mass model sometimes, but I think this is even worse because Ernest Mach has like 500 models, many models. So calling it mass model doesn't mean anything. He has just too many models. Anyway, so let me tell you what this model is. So in the Scotogenic model, you increase the number of fields in the standard model with just a new scalar doublet that typically people call eta. This is just a doublet of SU2 with exactly the same quantum numbers as the Higgs boson, as the Higgs doublet, sorry, but with a Z2 charge equal to -1. Okay, so again, we have to add this additional symmetry. And also you have 3 generations of singlet fermions that I call here N, also charged under the Z2. That is enough, as you will see in a moment, to produce neutrino masses and also dark matter. And actually, that is the reason why this model is called Scotogenic. So according to people that speak Greek, I don't, skotos in Greek means darkness. So this word, Scotogenic, means generated by darkness. So as you will see, neutrino masses somehow come from the dark sector. That's why this model was called like that. I think this is a name that was invented by Ernest Mach, and I think it's very catchy, a very good name. Okay, so with these fields, you can write down several Yukawa couplings, or one Yukawa coupling, sorry. This one here. By the way, Antonio, can you see the arrow when I move it?
I can
yes?
see.
Okay. Okay. I was worried that I was mentioning the arrow and you cannot see it. Okay, thank you. So you can write down this Yukawa coupling, but you should know that this Yukawa coupling doesn't involve the Higgs doublet, which is capital H, but eta. And this is because of the Z2 symmetry. So the coupling with H is forbidden by the Z2 symmetry. Also, you can write down a Majorana master for the singlets and many scalar potential couplings like the ones that I have written here. Okay.
Question.
And so, sorry, there was a question?
I have a question. If you, the master they are putting for this extra singlet, I think, right, the 3 extra singlet, that could in principle be non-diagonal, and you will have some seesaw for that also, right?
Yes, that's correct. I assume that I'm working in the basis in which it is diagonal already. Yes, that is correct.
That would provide another sort of suppression that could be useful, right?
In principle, yes, but you can always go to the basis in which this matrix is diagonal. Just rotating ends, you can make this matrix diagonal. And then all that goes to the Yukawa.
Mm.
So it's a particular choice of basis, if you want. But in principle, yes, it could have off-diagonal elements in general.
Okay, thank you.
Thank you for the question. Okay, so let me copy again the scalar potential in the next slide. I have it here because I would like to comment a little bit what happens in the scalar sector of the model. So if we just look at the eta fields, you know, eta is a doublet, so it has hypercharge 1/2. That means that you have a scalar that is charged and a scalar that is neutral, electrically charged and electrically neutral. The electrically charged scalar is here, eta plus minus. And then for the electrically neutral field, I can split it into the real and imaginary components, eta r and eta I, and I can calculate the masses for all of them. Okay, I did the exercise, and this is the result that I get. And I wanted to observe something that is very important for the model, which is that the mass difference between the real and the imaginary components of eta 0 is controlled by just lambda 5. Okay, this coupling here that I put here in red, because it's very important, is what controls the mass difference between the real and imaginary components of eta 0. And this has a very important impact on neutrino masses, as I will comment later. Actually, I will comment now. So this is the neutrino mass diagram, okay? And first of all, I should mention that the neutrino masses are forbidden at tree level because, as I said before, the Yukawa coupling is cannot be built with capital H, with the Higgs doublet, but with eta. Since the Higgs doublet gets above, that would generate a Dirac mass term, but that is forbidden by the Z2 symmetry. Eta doesn't get above, so by assumption, you don't get a Dirac mass term for the neutrinos. For that reason, neutrinos are massless at tree level, and their mass is only generated at the one loop level. The particular expression for the neutrino mass is not very illustrative, but it looks more or less like this. It's proportional to lambda 5 because you need this coupling here. and of course to the Yukawa couplings that appear in the vertices and inversely proportional to the mass that is here. This should read Mn, sorry, instead of Mr. Never mind. And you can see here that all the particles inside the loop, eta 0 and M, they are all belonging to the dark sector. They have Z2 charge equal to -1. That's why Ernest Mach said that this model generates neutrino masses from the darkness, because the loop is made by dark particles. It's kind of poetic way to see the model.
So you have several dark particles?
Yes, we have several of them. This is an important point.
Which one is the more stable? I mean, what?
Only the lightest one is stable, yes. Yes, I will comment on dark matter in I think it's the next slide, or the one after the next. Thank you. But actually we have several also inside the loop, because actually eta 0 is not a mass eigenstate. What you have inside the loop is eta r and eta I, the real and imaginary components. And it turns out that they come with different signs, with opposite signs. And they cancel. If their masses would be the same, they would cancel exactly. So that's why lambda 0 is important. As you probably remember, the mass difference between these two particles is controlled by lambda 5. That's why lambda 5 is a crucial ingredient in this model. And the most elegant way to realize about the importance of lambda 5 is to see that in the limit in which lambda 5 is 0, lepton number is exactly conserved in this model. That's why you need a lambda 5 that is different from 0 to generate Majorana neutrino masses. So this is one example of what I explained before of a symmetry protected suppression mechanism. So you have some parameter that is very small that needs to be non-zero to get neutrino masses. So that's why in the mass formula for the neutrinos, you get this lambda 5 proportionality that is very important. Why is that important? Because that allows you to have large Yukawa couplings and not too heavy singlet fermions, and still get neutrino masses in the correct order. So you would expect a very rich phenomenology in this type of models. And now I come to dark matter, as Professor Smith was asking. So the lightest of all the particles that are charged under the Z2 symmetry is completely stable. And therefore, it could be, if all the other ingredients are met, a good dark matter candidate. And you have two viable options. One option is that the lightest particle is a neutral fermion, one of these N's. So let's call it N1, the lightest of them. And in this case, this particle is a pure singlet. It doesn't have any gauge interaction. So it can only be produced via Yukawa interactions. For that reason, if you want to generate the correct amount of dark matter in the universe, you need largest Yukawa interactions. They cannot be very small. If they are very small, you don't produce enough dark matter in the early universe. And this is potentially dangerous for lepton violation, because when the Yukawas are large, you induce processes like mu2e gamma and things like that at very high rates. Since there are very strong constraints, you may wonder whether this is compatible with the current bounds. So this version of the model with a fermion dark matter, as I will show in a moment, is okay, but there is some tension with lepton violation. The other possibility is to have scalar dark matter. In this case, the lightest Z2 particle is either eta r or eta I. And this is much easier. Why is that? Because eta has gauge interaction, it's a doublet. Therefore, you can produce this guy in the early universe without any problem. You don't need large Yukawa couples, you can make them small, and dark matter is not affected by that. This is good and bad. It's good because it makes your life simpler, but it's bad because you lose the possible connection between dark matter and neutrinos via lepton violation. It becomes like two different things that can be worked out independently, which still is very nice, but the connection is not that tight. So you lose ways to test the model, which is a pity, but it's perfectly fine from a phenomenological point of view. And now I would like to comment on something that was a very recent surprise for me. And I'm kind of embarrassed not knowing about this paper because I have been working on the Scotogenic model for many years. But I was not the only one that didn't know this paper. So, as you know, the paper by Ernest Mach proposing the Scotogenic model was written in 2006. And very, very recently, only in June this year, this paper by a Chinese author called Xijian Tao was discovered. And it's curious because it's just the Scotogenic model, and it was written 10 years before, in 1996. So if you look at the paper that you can find very easily, you have here the reference. The paper contains exactly the same model with exactly the same Lagrangian. It even contains the neutrino mass diagram, and it even discusses dark matter. So it's funny that people rediscover the same model again and again. And in this case, I'm pretty sure that Ernest Ma discovered the model again because of its simplicity. But it's very unfair for the first author because that guy was only cited for the first time in June this year, and it has been cited since then only once again. So it has a total number of citations of 2, whereas Ernest Ma has been cited more than 1,400 times since he put out this paper on the Scotogenic model. So I find it very unfair for the first author. I will try to cite him from now on, but I'm pretty sure he will never catch up with Ernest Ma's paper. I mean, the difference is just too large. I wanted just to make this comment because it was, for me, it was very surprising to see this paper. Anyway, this was just a curiosity. Let me continue. So I already mentioned that lepton flow violation may be an important role. And this is something that is not only a feature of the Scotogenic model. This happens in many cases. Actually, every time you have a neutrino mass model, you tend to use lepton flow violation to learn about the origin of neutrino masses. And sometimes this connection is not possible, but in the particular case of the Scotogenic model, it is. So you can actually use lepton flow violation to learn something about the origin of neutrino masses in the Scotogenic model. And this is something that was known for many years. And actually, processes like mu to E gamma, tau to mu gamma, and tau to E gamma were computed in several papers. You have here the diagrams for this process. It's a very simple calculation, well, kind of simple, because it's just one operator. It's a dipole contribution. So after you do the calculation, you just get some result that depends on the Yukawa couplings times some loop function that is typically called F2. And that was known. And actually, my interest in this model started 10 years ago because this was the only process that was computed in the Scotogenic model. But as you know very well, there are other lepton flow violating decays. For example, you may have processes like a lepton going to 3 leptons. So, for example, mu minus going to E minus, E minus, E plus. So this breaks also lepton number, sorry, lepton flavor, not lepton number, lepton flavor, and it's a complementary process. So together with my collaborator Takashi Toma, we did this calculation some years ago, and there are some new diagrams that you have to consider. In particular, you have these box diagrams here with n's and etas inside the loop. And I mean, it's not very important, the result that we got, but you get something like this, again, proportional to the Yukawas, now to 4 powers of the Yukawas, times some loop functions that we call D1 and D2, that depend on some mass ratios. So not very important. I just wrote it here for illustration. And also we consider mu-to conversion in nuclei, which is also a very interesting process. And the difference with respect to the previous one is that in this case, you don't have boxes because the inner doublet does not couple to the quark sector. So eta does not couple to quarks. So you cannot have boxes. You only have this type of penguins, which are very similar to the ones you have for mu-to gamma. So in a way, this adds something, but not too much to the processes you had already. We studied, just for illustration, I show you here some plots. We studied the phenomenology, and here you have an example for some particular choice of parameters, very particular, fixing the mass of the eta doublet to 1 TeV and lambda 5 to 10 to minus 9. We studied what happens with normal and invented hierarchy for neutrinos. So the red points correspond to mu to 3e, the blue points to mu to E gamma, and we plot them as a function of this mass ratio, mn divided by m eta plus square, okay? And normally, as you can see, the blue points, so mu to E gamma, is above mu to 3 by typically 2 orders of magnitude. And this is what you expect in many models. This is actually a very common feature of many models. But it is interesting that in some regions, you may have actually the opposite hierarchy. Mu to 3 may have a larger branching ratio. This happens for normal and for inverted hierarchies. So it is possible to have mu2 with a branching ratio that is larger than mu2 gamma. And you may wonder, okay, yes, but this happens for this particular value that is not interesting because it's excluded experimentally. And you will be right. But, yeah, sorry, go ahead. Yes.
Yeah. Your left on prior violation comes only from Majorana mass? Is that
from the Yukawas. It comes mainly from the Yukawas. For example, here you have the Yukawas that appear in the vertices of the boxes.
That gives. You get Majorana masses, I mean, also?
Also, we have Majorana masses, yes.
So, come from there, essentially.
Okay, but we are working in the basis in which this is diagonal. So all the flavor violation is in the Yukawas. But it's the same. We could do the opposite and it would be the same. We cannot distinguish, yes.
Mm-hmm.
Yes, we can do that. We can take the Yukawas diagonal and put the flavor in the Majorana mass. That is possible and it's the same, yes.
Okay, thank you.
Well, thank you for the comment. So I was just about to mention that all these values can be reduced or increased by changing the value of lambda 5. So here these horizontal lines are the current limits, but I can make this region, which is excluded in this plot, I can make it okay, I can make it accepted just by changing the value of lambda 5. If I take a larger value of lambda 5, all the Yukawas are reduced globally, it's a global factor, and then I can get these points and put them here. So this region can be allowed just by changing lambda 5 without altering anything else. So this is an observation that we made in that paper that we found interesting, that the phenomenology is actually very rich, and you can have many processes and not only mu2 gamma, which is typically what people consider. And actually, also related to this, and already mentioned before in my talk, when you have fermion dark matter in this model, you may have problems with lepton flavor violation. As I already explained, this is because fermion dark matter requires large Yukawa couplings in order to get the correct relic density. And at the same time, when you have large Yukawa couplings, you may induce large LFB rates. So typically, this leads to tension. In order to study this, we studied with my colleague Carlos Llaguna, we studied what happens in this scenario regarding dark matter, and we made these plots by scanning randomly in the parameter space. All the points that you can see here are okay regarding mu2 gamma, are okay also regarding neutrino masses, of course, and are okay regarding dark matter relic density. So they fulfill the 3 bounds. But they are plotted in the plane branching ratio for mu2 gamma, branching ratio of mu2 or the conversion rate of mu2 in titanium. Okay? The horizontal lines are the current limits. The vertical line is the current limit for mu2 gamma, so everything is excluded because it's below. And the dashed lines, both horizontal and vertical, correspond to future limits. So you can see that there are many points. For example, on the left, every point that is above this line is excluded because it gives mu2 too much. So the branching ratio is too large. But there are a few points which are below. So there are points that are allowed. The same happens on the right. So both plots basically give the same message. So the conclusion is the scenario is still alive, but it is very constrained. So most of the points are actually excluded by these branching ratios. Also, you can see that if we don't observe anything and all the points get excluded in the next round of experiments, when we reach these sensitivities here, then the complete parameter space will be ruled out. However, people have found ways out. One way out is to have co-annihilation. You know that when two particles have very similar masses, you increase the annihilation cross-sections, and then you can get an enhancement that allows you to have large Yukawa couplings, small Yukawa couplings, but a very large cross-section. This is one possibility. It is known to work. Also, you can play with textures. Also, there was a recent paper discussing phase transitions that can help. So there are ways out. But I think it's fair to say that this is a very constrained scenario that by default, it's very hard to make it work. You need to work a little bit to make it work. Okay, so with this, I concluded this part of the seminar about the Scotogenic model, and now I want to go beyond. I want to see what happens if I take this minimal idea by Ernest Ma and also previously by Tao and see variations of it. So I will play with the Scotogenic model and consider variants of many different types. So this is why I call it from model to paradigm. You can consider this specific model or you can consider a class of models.
I have a question.
Sure.
How does this simple model sort of go into other things like G-2 and other things that you can, and also variogenesis or leptogenesis? I mean, how does it do there? I mean, what is it? It's okay because you can put more constraints that you have put already.
Yes, that's a very, very good question. So for the G-2 of the muon, I can comment a little bit later. So the minimal model doesn't work. The minimal model, because the G-2 of the muon, you need a chirality flip because it's a chirality breaking operator. You need to go left from right. And you don't have such chirality flip in this model. You need to use the muon mass, and that is known to give a very small contribution. So the minimal model doesn't work. You need an addition to the minimal model. And if I have time, I will comment later on that. For variogenesis or leptogenesis, as you said, this has been studied, but I never did it myself. What I know is that you can make it work, but you need some sort of resonant effects, some sort of resonant leptogenesis. Otherwise, again, it's very hard to make it work for leptogenesis. You need to use these small mass splittings to make it work. And this was studied many years ago, as far as I know, by several people. I forgot their names. I can find the paper later if you're interested.
Okay, thank you.
Thank you. So, as I said, so there are many ways in which you can change the model and explore new paths. For example, in the minimal model, you have one eta scalar and 3 singlets, but this is just a choice. You can use different numbers of generations. Also, you can choose different representations under the gauge group. In this case, you have just a doublet and a singlet, but you can use different things. Also, this minimal choice of representations is very nice, very economical, and is already good enough to work, but you may consider the addition of additional Scotogenic states. And finally, in the original model, you consider explicit lepton number violation. So the combination of the Yukawas, the Majorana mass for the singlets, and lambda 5 breaks lepton number explicitly. But you can consider variations in which the breaking of lepton number is spontaneous and not explicit. So there are many ways in you can vary a little bit this model and get a very different scenario. And that's what motivates me. The idea that you can modify something and get something that is already very different, even though the modification was very small. So I will now give you a couple of examples of that. And if you have more questions or you are curious about some of these ideas, we can comment on them later. So the first example that I wanted to discuss is some work that I did in collaboration with my colleagues Valentina de Romeri and Miguel Puerta here in Valencia a couple of years ago. And we call it charged Scotogenic model. You will see why in a second. Actually, this model was not proposed by us. It was already presented in the literature by these people here, Aoki, Kanemura, and Yayu. And actually, it's a very simple variation of the original Scotogenic idea. Here, in this model, you have, again, eta. It's the same eta as in the Scotogenic model. But now you have a second doublet that they call capital phi. So capital phi is a doublet of SU2, but now hypercharge is not 1/2, but 3/2. Because of that, this doublet contains a doublet charge scalar and a singlet charge scalar. And that was actually the main motivation for them. In this paper, they wanted to study doublet charge scalars at colliders. So they constructed a model with this particle in the spectrum in order to study this particular phenomenology. And finally, instead of singlets, they have vector-like charged fermions. So we have 2 generations You can do it with 3 if you want, but 2 is okay, it's already enough. 2 generations of vector-like fermions, which are singlets of SU2 and have hypercharge equal to -1. So they are electrically charged. And all of them, as usual, charge under the Z2 symmetry. With this, you can write a Dirac-Mass term for the vector-like fermions, because they are vector-like. You can write new Yukawa couplings, and it's interesting to note that you have 2 additional Yukawa couplings, one with the left-handed part of this vector-like fermions, this one here, and one with the right-handed part of this vector-like fermions, this one here. The scalar potential of the model is kind of complicated because you have many scalars. And again, I would like you to pay attention to this parameter here, kappa, which is a quartic coupling that involves all the scalars in the model. So phi, h, eta, and again, h. Okay. So if now I pay attention to the Z2 odd scalars, again, eta 0, exactly like in the Scotogenic model, we can split into eta r and eta I, and their mass difference is controlled by lambda 5, just like in the Scotogenic model. For the charged particles, you get something new. Before we just had eta plus, but now we have eta plus and phi plus. And they mix in general, and their mixing is proportional precisely to kappa. Very important coupling. And finally, as I already said, there is a doubly charged scalar phi plus plus, which is a bit exotic if you want. And neutrino masses, they proceed very similar to the usual Scotogenic model. They are forbidden at trio level due to the Z2 symmetry. They are generated at the one loop. But now the difference is that the particles inside the loop are all electrically charged. That's why we call it somehow a charged version of the Scotogenic model. So both the fermions and the scalars are charged. Another particularity of this model is that the couplings that appear here in the vertices are different, are independent. So YL and YR are 2 independent Yukawa matrices. For that reason, the neutrino mass formula looks like this. So you get this combination here, YL, YR, YR, YL, the symmetric combination, because the matrix has to be symmetric. And for this, I wanted to comment on something called the master parametrization that we created some years ago. And you probably are familiar with the Casas-Ibarra parametrization that is used, for example, in the type 1 seesaw. The master parametrization is a more general version of that is also valid when the 2 Yukawas are different. So this particularity has to be taken into account if you want to do a numerical study. Okay, let me proceed. Dark matter. So in this case, some of the new particles are electrically charged, and therefore they cannot be used as dark matter candidates. So the fermions cannot be dark matter candidates, and in the scalars, you cannot use the scalars that are electrically charged. You can only use eta r or eta I. As explained already, in this case, you can produce this particle in the LA universe without any problem because it has gauge interactions. But we wanted to answer the following question. This is not the Scotogenic model. There are new particles. In particular, there are new charged particles. Is there any difference with respect to the Scotogenic model because of that? So this is what we wanted to investigate in this particular work. And I will show you the result. For that, we did some analysis. We consider somehow a very agnostic random scan of the parameter space. We had to fix some parameters, but many of them were allowed to be completely free in a wide range. We used several of the popular tools in the market to do the numerical analysis, and we consider many constraints. Of course, we consider neutrino oscillation data. I will make a comment on the next slide. We consider electron flow violation, electroweak precision data, dark matter and LHC searches, Higgs decays, because, you know, when you have electrically charged particles, the Higgs to gamma gamma, for example, gets modified. So we had to make sure that this is not modified too much, that is within the limits. And we also had to consider, this is a technicality that I don't have time to explain too much, the lifetime of the electrolyte test, the Z2 state. And let me comment on neutrino oscillation data. I made this comment already, but let me be more specific. I mentioned already here that the neutrino mass formula involves 2 different Yukawa couplings. So this is why this master parametrization is very useful. And here I wanted to give you the formula. So for people that are familiar with the Casas-Ibarra parametrization, I'm pretty sure that when they look at this, it kind of reminds them that to that formula, but it's a bit different. So U and capital D, this is common to the Casas-Ibarra parametrization, but you have here some additional matrices that take into account that these two Yukawa couplings, Y1 and Y2, might be different. Okay, so I won't discuss this any longer, but if you're interested, you can have a look at these papers that I cite here. And this might be useful if you have a model with this property, two different Yukawa couplets. Okay. So these are the results of our numerical scan. Here you have the dark matter relic density as a function of the dark matter mass. So eta R is the mass of the dark matter particle. And in this plot, all gray points are excluded due to some constraints. The blue points are okay, but they lead to underabundant dark matter. So you need more dark matter from other sources. So that's okay. And the purple points not only are allowed, but also produce the correct amount of dark matter. So the first observation is that this region here, where dark matter is fully accounted for, is the same as in the inner doublet model. So no surprise. So the same region in parameter space that you would expect from the inner doublet model. Fine, that's okay. But the second thing we noticed is that we had this point here with this feature that we didn't understand at first. You know that when you have some sudden drop of the dark matter relic density, that typically means that there are two particles which are very close in mass, or there is some relation between their masses, and that increases the cross sections in the LA universe. However, that was not the case here. That is the case here and here, but not here on the right. We wanted to investigate what happens here, even though these points are excluded. And we actually find out that those points produced a strong decrease in the dark matter relic density because of this coannihilation here. So this process among charge states with H1 and H2, the two charge scalars, mediated by the charge fermions into neutrinos, this process was actually very relevant in that region of parameter space. And you may remember that our dark matter particle is eta 0, so a neutral scalar, which is not very different in mass in our scan to H1 minus. So because of that, the influence on the dark matter relic density was very large. However, why were these points excluded experimentally? Because for this process to be effective, you need both Yukawa couplings to be large. So when that happens, you have problems with lepton ferroviolation. This being said, we investigated this a bit more, and we found that with some fine-tuning, you can avoid the bounds from lepton ferroviolation. Here in these plots on the right, you have the branching ratio of mu to gamma in blue, and the dark matter relic density in green. And you can see that for some parameters, for example, this K12 is one of the elements. Sorry, let me go back. Of this, I don't have it here, sorry. Anyway, it's one of the elements of one of the matrices that appears here that I didn't define because I didn't define all the matrices. Sorry for that. But just one parameter that you can play with in your parameterization of the Yukawas. So by playing a little bit with this parameter, you can suppress very strongly the mu to gamma branching ratio. And the dark matter relic density is not affected too much. So it's very easy to make this scenario to work by tuning the parameters a little bit. So it's not very attractive, but it's actually possible. Okay, I will now move to a different example of a variation of this setup. Maybe it's a good moment to ask you have any question about the first example that I showed. If not, I will continue.
Let me try to clarify. You're just using this initial model and putting more particles. I mean, sort of adding particles in different representation, whatever.
Yes.
And trying to find which of those is the best dark matter particle. But
yes,
your symmetry is always the standard model plus the C2. That's it.
That's correct. Yes.
Because that way it seems to me that you're never going to be able to, for example, understand the masses of the other leptons or the quarks or whatever. I mean, it's impossible in this mechanism.
I totally agree with you. So these models do not provide any insight on flavor problems. I totally agree with that. So you can see them as a part of a bigger model where that question is also addressed. But we don't address that question. You are right.
Okay, thank you.
Yes, yes.
Avelino, in that model with doubly charged scalar, is it possible to get the correct sign for the G-2? Because the usual Scotogenic model, the vertices are the same, so it's negative sign. But here, I suppose that in principle, you could fit the correct sign.
It's a good question. I don't know the answer. It may be possible. Not only because you have the doubly charged scalar that gives you an enhancement, but also because you have this vector-like mass that may help you to have this chirality flip.
So this is very nice because the chirality flipping occurs in the internal fermionic line, so G-2 will be enhanced.
Exactly, I think so.
Without having two light charged scalar masses.
Yes, yes. But to be totally honest, I don't know. I never studied that. So maybe it doesn't work for some reason. But potentially it looks attractive. It could be possible, yes.
It seems that it may be possible to work, or at least this could be put some constraint on the model on top of the neutrino masses.
Yes,
and
yes,
on
yes.
that
No, very
value.
good comment, Antonio. Very good comment. Yes. Yes, but I never studied. But I guess I think I agree with you. I think it's very likely that it works. Thank you.
You're welcome.
Okay, so let me now talk about a different way of extending this setup. And this is something that I did with my student Pablo Escribano and also with Diego Portillo Sanchez, who visited us. He's working in Simvestat. He's a student there in Mexico. He came to Valencia for some time, and together we work on this project. And we put 2 papers on the archive. The first one with only with Pablo, the second also with Diego. And in this case, the idea is more model building driven, if you want. So let me explain what I have in mind. So I already mentioned several times that in the Scotogenic model, we take a small parameter, a small lambda 5 parameter. This is totally natural. And this is something that was discussed by Toft in the 80s. The reason why this is natural is because when lambda 5 is exactly 0, lepton number is restored. So any correction to lambda 5 due to symmetry has to be proportional to lambda 5 itself. So if this parameter is small at some energy scale, it will always be small. So that's fine. It's okay. However, there is no explanation for that. It's an ad hoc assumption. And you may find that a bit, I don't know, disturbing to have this ad hoc assumption. The second thing is that the set to parity that appears in the Scotogenic model is also ad hoc. It doesn't come from any fundamental principle. So we wanted to study ultraviolet extensions of the Scotogenic model where this is addressed. So in order to understand this better, let me show you an example of a model that can solve these 2 problems. This is the first example we found, but let me mention that if you don't like this model for some reason, in the second paper, we classified all possibilities. Together with Diego, we found many models that can do exactly the same job with minimal variations. But this one, I think, is very illustrative. So I take the Scotogenic model and I extend it with 2 new fields. First, I have one triplet that I call delta, scalar triplet. It's a triplet of SU2, hypercharged 1. You can have it here. So you have a doubly charged scalar, a singly charged scalar, and a neutral scalar. And I also have another singlet. This singlet is a singlet of everything. So it's singlet under SU3, singlet under SU2, and singlet under hypercharge. So 0 hypercharge. And also, now I don't have a set to symmetry. Instead of that, I have lepton number, a global symmetry, lepton number, that I consider to be exactly conserved. So all the Lagrangian will conserve lepton number. And I assign these particular values of lepton number to the different fields in the model. For the leptons in the standard model, I have no choice. They are leptons, so they have lepton number equal to 1. For the Higgs, I also have no choice. It's lepton number equal to 0. But for the new fields, I have freedom. And I have found that this model works if I take these particular choices. 1/2 for M, minus 1/2 for eta, minus 1 for delta, and 1 for S. With that, I can construct the Lagrangian, which is super large. No need to read it completely. Let me just focus your attention on this Yukawa coupling here. This is the same Yukawa coupling that we have in the Scotogenic model, nothing new. But also now, the Majorana mass for the n singlet is forbidden due to electron number, but you can have a new Yukawa coupling involving this singlet S and proportional to some Yukawa coupling called kappa. Also, there are some scalar potential parameters that are relevant, and you may think that there are other terms allowed by the symmetries, but actually this is all you may have. All the other terms are forbidden by lepton number, which we take to be exactly conserved. Now, what is the idea we have in mind? The idea we have in mind is that delta will be assumed to be much heavier than any other state in the model. Therefore, delta lives at some ultraviolet scale, m delta.
This U1L is spontaneously broken.
It will be spontaneously broken, yes.
So you have a Majorana or Galton boson there?
Yes, we have a Majorana. Yes, exactly. Yes,
Okay.
I will explain that in a moment, but yes, I can tell you already that you are completely right. We will have a Majorana. Okay, so I will take m delta to be very big, much larger than any other scale. And then you know that one typical technique to work in this type of situation is to integrate out the heavy particle, in this case delta, and then write down an effective theory where I keep all the light particles and contributions up to dimension 6 in the fields. And they will appear suppressed by 2 powers of m delta. Okay? And the idea we have in mind is that this way we will recover the Scotogenic Lagrangian plus some extra terms. And with these extra terms, we plan to solve these theoretical problems that we think the Scotogenic model has. So this is the result we get after integrating out delta. Our calculation is very simple because we just consider 3-level integration. So we took the 3-level integration of delta, and this is the result. Well, you see already that some terms appear suppressed by 1 over n delta square. This is a dimension 6 operator. Also here you have a dimension 6 dimension 6 operator, and so on. Okay, well, actually this is dimension 5, dimension 5 operator. Also here you have another contribution that goes like 1 over m delta. And the first thing that I wanted to point out, as Professor Smith already advanced, after symmetry breaking, lepton number will be spontaneously broken because S will get a BEF. That breaks lepton number because, let me remind you, S has lepton number equal to 1. So lepton number is broken when S gets a BEF. However, you can see very easily from this Lagrangian that actually lepton number is broken, but it's not broken to nothing. It's broken to a set-to symmetry. So this is very nice because we recover the set-to symmetry of the Scotogenic model. Exactly the set-to symmetry of the Scotogenic model appears automatically after symmetry breaking. And the second thing that is very nice is that you can see that in our original Lagrangian, there was no lambda 5 coupling because lambda 5 was forbidden by lepton number. But after we integrate out delta and we give a BEF to S, this coupling here eventually becomes lambda 5. But the resultant lambda 5 will be given by this combination here. And since we are assuming that m delta is much larger than any other scale in the model, automatically lambda 5 by assumption will be a very small coupling. So we have solved also the other issue that we had in this model, which is what we wanted. If we look at neutrino masses, they look like this. So you have, this is the diagram, if you want, in the UV theory, where delta is propagating here. And when you integrate out delta, which is basically when you collapse this line into a point, you get this diagram on the right. So this is basically 2 versions of the same diagram at high energies or at low energies, okay? And you see that apart from the fact that you have this scalar singlet here, that you need this guy to get a BEF, it's essentially the diagram for the Scotogenic model. Now, let me talk about the scalars because I will come to the comment that was just made. If I split into, again, real and imaginary components, if I look at the even parts, so the CP even components, the real components, I get 2 states with a mass matrix that looks like this. And when I diagonalize it, I get 2 mass eigenstates. One of them will be identified with the Higgs boson that was discovered at the LHC, but there is a second guy that is heavier, and they are mixed. Since the LHC data tells us that the particle that has been discovered has properties that are very close to the standard model Higgs boson, we have to make sure that this mixing angle is small, okay? So we have a constraint on this mixing angle, cannot be very large. In particular, lambda 3s has to be small. Otherwise, we're in trouble with data from the LHC. But that's fine. We can take this parameter to be small, and that's okay. And now, and this is very interesting, as Professor Smith said, so if we now look at the CPO scalars, we see that there are again two states. One of them is the typical Boothby-Goldstone boson that is absorbed by the sea and becomes the longitudinal component. So this is not a physical state, but there is a physical Goldstone boson, the so-called Majoran, associated to the breaking of lepton number. So in this model, let me say it again, there is a massless particle, a Majoran. So we have to make sure that this guy has suppressed couplings to matter. Otherwise, we are in trouble with experimental constraints. And actually, we look into this. For example, we calculated the one-loop coupling of the Majoran to a pair of charged leptons. So in this model, the Majoran couples to charged leptons also at the one-loop level, not at tree level. We did the calculation. We got this result here. It's not very important, but you see that it depends, of course, on the Yukawa couplings and on some combination or loop function that depends on the masses of the particles in the loop, n and eta. And on the right, I show as a function of the BEF that breaks lepton number, the branching ratio of mu to e Majoran, so the decay of a muon into an electron and a Majoran. And you see, for three different particular choices of the parameters, that in some cases, you get results that are above the current limit. So this is an important constraint that has to be taken into account. But as you can see, if you increase this BEF a bit, so if you go to 10 TeV or so, everything is allowed, okay? If you are below to 10 to TeV, you have to choose the correct values of the parameters to make sure that you are not excluded. But it's very interesting that you can get a large branching ratio here in this model. Also, and sorry, I forgot to mention here, also with the same calculation, you can compute the couplings to electrons, muon, and tau, the diagonal couplings. And those have to be made small because there are very strong astrophysical bounds, which I didn't include here in the slides, but of course have to be taken into account. And other processes that are induced by the presence of the Majoran is the invisible decays of the Higgs into a couple of Majorans. And the coupling is given by this expression. And since there are limits on that, we know that this coupling here, lambda 3s, cannot be very large. And this is something that we already knew from mixing. So we estimate that in order to comply with the bounds, you need something that is not much larger than 10 to minus 2. And finally, let me comment on dark matter. Again, since we have a Majoran, all the production mechanisms in the early universe may be altered. And this might be particularly relevant when you have fermion dark matter. This was studied for the first time by Bonilla et al. And I think I saw Roberto in the audience. Roberto is also an author. Roberto Lineros is an author of this paper. And we studied again the problem a bit later, and we found very similar results. And we found that actually there are additional production mechanisms for dark matter in the early universe thanks to the presence of these new scalars. So it could also help to alleviate the problems with fermion dark matter in the Scotogenic model. And this is the last slide I have before the conclusions. As I already said, this model that I presented, this ultraviolet extension, is just one particular example. There are many that you can construct. We actually, in this second paper, we consider all the possible topologies that eventually lead to the Scotogenic model. So I give you here a couple of examples. They are just two examples. They are not particularly important, just two examples. And many ultraviolet extensions with this feature. So if you're interested in this idea, but you don't like this particular model, you may find a variation that is better for you, okay? There are many variations with this idea. And with this, let me just conclude. And now, of course, we have time for discussion if you want. I wanted to somehow convince you that neutrino masses and the Scotogenic model are very interesting topics. And in particular, I like the Scotogenic model because it's very economical. Very simple. With very simple things, you just get neutrino masses and dark matter. However, the Scotogenic model, the original one, is very interesting, but it's just an example. And I think with these two particular variations that I consider, that it's attractive to see that just small changes in the definition of the model may lead to very big impact in the resulting phenomenology. In the first case, we found that with the addition of these additional charge scalars and fermions, you have novel annihilation processes, but you have some required fine-tuning to use them to get additional regions in parameter space for that matter. And in the second example that I showed, I explained that in these ultraviolet extensions, in addition to the Scotogenic model at low energies, you get also additional scalars. In particular, you get a Majoron with novel phenomenological predictions. So I hope you found this interesting. I think the Scotogenic model is very nice. And I thank you for your attention. Muchas gracias.
Thank you very much, Avelino, for the very nice and complete talk. Question from the audience?
Yes, I have a question. I promise it's going to be the last one anyway.
No problem. It's fine. Thank you.
Yes. In the last transparency, you ended up with some operators that were sort of look like, 4 fields, 5 fields, and so on. And
Yes.
these are going to be there's going to be higher dimensional operators seem to be. So they're going to be down by a certain scale, and they're going to be non-normalizable, obviously. I see some problems with those, because they're going to be very small, because they're going to be, there's some scale in which they're going to be sort of important only.
Yes, you are totally right. Actually, for example, if you look at these terms here, in many cases, they are just very small corrections to something that you already have in the original Scotogenic model. For example, this one here, this would give a small correction to the quartic coupling of the Higgs, but it's just a very small correction. It's totally irrelevant. Since M delta is very large, this is a very small correction. Also here, you have a correction to the quartic coupling of eta, and I think that's it. But there is one term that you didn't have in the original model before integrating out delta, which is this one here. So this term, this dimension 5 coupling, because you have 5 scalar fields here, this is not present in the original model. So this is not a correction, it's a total new term. And this has to be small for phenomenological reasons. You need lambda 5 to be very small. And you get it automatically small from the construction. So this is what we wanted in this case.
Okay, thank you.
Thank you. Thank you for the questions. Very, very nice questions. Thank you.
More questions from the audience? Avelino, and regarding the constraint from electron mode conversion in this UV completion of the Scotogenic model, they differ significantly from the simplest version of the Scotogenic model, or they are more or less similar?
I think they are similar. Because basically when you integrate out delta, you are left with just the Scotogenic model, and that's it. The only thing that may be relevant is the Majoron, because you may have also a Majoron leading to mutual conversion in nuclei, but since you have to comply with the bounds from mutual gamma and so on, I don't expect this to give a very large contribution to mutual conversion. So it would be very similar to the result you have in the original Scotogenic model.
So the difference will be from the decay of mu to E and Majoron. Will be, for example,
Yes.
the Mottingham signature, which will differentiate that model from the other one.
Yes, because this is completely new. You don't have this in the original Scotogenic model. You have it here in this variation, but not in the original model. Yes.
I see. And from the production mechanism of this electrically charged and doubly charged scalar, have you analyzed that part, the production mechanism, the cross-section of the LHC or the upgrade of the LHC?
You mean in the other model, in this one here,
the other one, yes, with
Yes.
Exactly, with the doubly charged scalar.
Yeah, unfortunately, I don't have any slide here on that, but actually this is what these people here, Aoki, Kanemura, and Yagyu, they studied in 2011. So they studied particularly the doubly charged, the production of the doubly charged scalars at the LHC. It's just Drell-Yan production, normal Drell-Yan. And yeah, it was totally observable. I mean, this guy is a very clear particle, no, at the LHC, doubly charged.
I see. So it would be cross section of the order of, I suppose, few femtobar or maybe picobar, depending on the masses.
I don't remember the number, but probably yes. So,
Around
and
the
also
order.
the decay, I think if I remember correctly, they studied the decay to same sign leptons, which is a very striking signature because you typically don't have that in the standard model. You don't have any background for same sign leptons.
So this will be a smoking gun signatures. If
Yes,
this model
yes.
is this processing at the LHC could be, for example, indication of doubly charged scalar of that model, for instance.
Yes, yes, into mu plus, for example. Yes, yes.
Thank you, Avelino.
No, thank
More
you, Antonio.
question? More question from the audience? If there are no more questions, we thank Avelino again for the excellent talk and very complete talk. Thank you very much, Avelino, for the very
Thank you.
nice seminar.
It's a pity that I did it online. I would love to do it in Valparaiso, where I had a very nice time when I was there. So maybe next time I can do it in person. I would love to do that.
Yes, it will be great that you can come to Valparaiso and give the seminar in person and to stay some time for collaboration visit will be great.
That would be
Usually we
nice.
had here a biannual conference. There was in January of this year. So next to in about 2 years there will be the usual HEP workshop. Will be nice.
Yes. I got the yes. I hope next time I will be able to go. That would be
It will
nice.
be great. Thank you very much, Avelino.
Thank you, everybody. Thank you.
Goodbye.
Bye.
Bye.
Hasta luego, Antonio. Un placer
Hasta
como
luego,
siempre.
Avelino. Que estés muy bien.